Thank you. Thank you all for attending this talk, which indeed is about automatically deriving incremental type checkers using scope rules. This was worked on in collaboration with Antwerp and OOPSLA, who is my supervisor, who unfortunately passed away past April. But I think this work is exemplary of this vision of lifting complexity from the language implementer or the language designer to meta-language backends, which greatly influences the ease in which we can develop languages. So let's get started. I think most of us will agree that type checkers are useful components of compiler. However, implementing type checkers can be pretty hard, especially when a lot of non-lexical name binding is involved. You need to carefully stage all sort of passes over an AST, build up symbol tables, and propagate them properly. Because of this, type checkers can become complex pieces of software that take a lot of time to develop and to maintain. Therefore, I think we should take another route. Instead of manually implementing type checkers, we should generate them for more high-level specifications. And a possible way to do that is using the Statix DSL. So how does that work? So the language implementer or the language designer just writes a very high-level specification. The specification is then given to the Statix backend, which then emits a type checker. This type checker is fully functional and can be used to type check real-world concrete programs. However, there's even more that we can do with these specifications. We can also generate code completion services, do refactorings like renaming and inlining, and many other things, all for free for the language designer. And what enables this? Both at the specification level and at the Statix backend level or the implementation level, this is supported by scope graphs. Scope graphs are a graph structure that represents name binding, which allows us to model all sorts of complex non-lexical name binding patterns. So before explaining this in more detail, let me quickly list the advantages of this approach. First of all, it's easy. As a language implementer or a language designer, you only need to write a very high-level specification, and everything else is given to you for free. Secondly, we can be sure that all those services behave consistently. For example, it will not be possible that the code completion service will give proposals that later on the type checker will reject. Thirdly, because the specifications are pretty high level, we could assign a declarative semantics to them, which is independent of the implementation of, for example, the type checker. And this allows us to reason about our type checkers, for example, prove type soundness. However, this sort of abstraction comes at a cost. In this case, it is performance. The type checkers that we generate using these tools are pretty slow. And with slow, I mean taking over a minute to type check a medium-sized Java library. There are many ways to solve performance problems, but one of the most promising ones in type checking is making them incremental. So that's what I'm going to present today, and especially I'm going to demonstrate how scope graphs can help us to create type checkers incrementally in a language parametric way. Before diving into that, let me quickly demonstrate how Statix works and how high-level declarative the specifications are. In this slide, on the left side, there's a few type inference rules as you could find them in a paper. The one is just stating that every integer literal has type int, and the other one is saying that an if expression has a particular type t if both branches of the expression agree on that type t and the condition is a boolean. On the right-hand side, you see how you would express that in Statix, and actually it's pretty similar. There's a rule that indeed matches on integer terms and returns a type int, and there's a rule that matches on if terms, returns a type t, given the three conditions at the bottom of the rule hold, namely the condition should be a rule, and both expressions should also have type t. But these specifications on the right-hand side we can actually turn into executable type checkers. However, this still does not involve name resolution. Name resolution, as I said, we are using scope graphs for, and I'm going to demonstrate it with this small Java example where there are two classes where one class extends the other. In scope graphs, nodes represent scopes of a program. In this case, the scope S represents the global scope, so the scope of the whole project. In this project, there's a class A, which has its own scope for its body. This is represented by the owner scope A. There's an edge from scope A to S with a lex label to indicate that the global scope is the lexically enclosing scope or the lexical parent of A. On the other hand, nodes can also be used as declarations. That's the reason why we assign the name A to this scope, but that's also the reason why we have an edge pointing from S to A. This edge indicates that A is a declaration of a class in the global scope. Well, for class B, we have the same structure, a scope for it, and two edges pointing both ways. However, there's also the extends clause in class A. So how do we model that? First of all, observe that the A I marked red is a reference. So for a reference, we need to find a corresponding declaration. The way that's done is having a query in the scope graph, which starts at the node where the reference occurs and finds a path in the scope graph that resolves to the declaration that corresponds to this name. At this point, we can use the reference to the scope A to model the whole extends clause. And that's simply done by adding an edge from scope B to scope A. This edge will ensure that everything that's visible in scope A will also be visible in scope B, essentially modeling what extension means. So let's make this example a bit more interesting and add some declarations in classes. There's two fields where the initializer of field Y references field X via the class extension. So note that this reference is non-lexical. How is that modeled? Again, we have a scope for this declaration, which has an edge pointing to it with a var label to indicate that X is a variable living in scope A. And similar for Y in B. Now again, X is a reference modeled using a query which starts in scope B because X lives in scope B and finds a path through the scope graph to the corresponding declaration. And note how we did non-lexical name resolution in a way that's actually similar to the way we did lexical name resolution. Finally, scope graphs also support a notion of compilation units, marked with the dotted boxes. In this program, there are 3 units, one for each class, and a whole project unit. And parts of the scope graph correspond to parts of the unit. And it will become important later in this talk because we will incrementalize type checkers with compilation unit granularity. Okay, so as I said, we can actually use scope graphs to model type checkers in Statix. That's what I'm going to show now. In this constraint, just tells us how to type check a class declaration. And I will just quickly go over it and show how all those constraints correspond to the scope graph. So first of all, there's this new constraint. This constraint generates a new scope and binds it to the SCLS label, variable, meta variable. Secondly, we have this constraint that asserts that a particular edge exists, in this case from the class scope to the enclosing scope, which is the global scope. This constraint introduces a declaration. It assigns the name of the class to the scope, to the class scope, and ensures that there is an edge from the enclosing scope S to this declaration. Finally, we can use queries to look up the references. We can give all sorts of parameters to these queries to be able to model name resolution behavior of a very wide range of languages. In this case, our query will look for classes that have a parent name in scope S, and the result should be a singleton set with the scope of the declaration. And the reference to this declaration scope that we obtain is used to create this extension edge. And finally, we will use another constraint to type check the body. But note how we pass the class scope to this constraint to ensure that the declarations in the body of this class are actually type checked in this class's scope. However, as I introduced, this high-level abstraction comes with a cost in performance. There's just a lot of overhead into resolving these queries, And as I said, incremental type checkers are an important way to try to solve this. However, we do not have a generic approach to incrementalize type checkers because traditional approaches that you would find in, for example, build systems do not apply because many type systems have mutual dependencies which usual notions cannot generally deal with. In particular, it's a challenge how to track dependencies between units, especially mutually dependent units. And in this talk, I'm going to show how we use scope graph diffing to do that. And the setup is that each compilation unit has its own type checker, which upon a change in the program executes the pretty simple algorithm on the right. It will reanalyze the compilation unit when either its own AST changed or any query changed, because queries actually correspond to dependencies. However, this part is challenging. How can you verify in a whole project that a particular query that you as a type checker did is actually changed? Now I'm going to show that with this example. Again, we have three Java classes where there is a reference in class C, Y, which is intended to point to the declaration in class A, but it doesn't work for two reasons. First of all, class B does not extend class A, so actually X is not visible in class C. And secondly, the names do not match. There's a declaration of X, but the reference says Y. You can also see that in the scope graph. The scope graph looks quite broken because this program is just incorrect. So the programmer tries to fix this and first adds an extends clause to class A. And now the challenge is for each compilation unit we should decide whether we should reanalyze it. Obviously, that should be done for unit B because it's changed. But for unit A and unit C, it's not so easy. In this case, I will especially talk you through the process unit C goes through. So first of all, the unit B reflects this change in the scope graph. So we see that a new edge from B to A is added. Unit C observes this edge and sees that a new scope A becomes available, which, well, potentially might lead to some new declarations for Y. Therefore, it will execute a query starting in scope Y. However, this query will not result in anything because there's no actual declaration for Y, and therefore unit C decides not to reanalyze because the initial query that it did not change. So our programmer still sees the type error in unit C and goes on editing his program, and well, he changes the name of X in Y. Again, our system will then reflect this in the scope. And the way that's done is, of course, the declaration of X is removed, and there's a new declaration for Y in the scope graph. So again, unit C will consider whether it needs to be reanalyzed or not. So first, it observes that a declaration got out of scope. However, because this declaration was not in the environment, that's not a reason for unit C to try to reanalyze. In addition, there's also a new declaration. And yes, this declaration actually changes the answer to the query for Y. Therefore, unit C will, upon this new result, decide to reanalyze itself and observe that now the program is type correct. In a nutshell, this is the core idea of the algorithm that we implemented. There's a bit more to it. We found ways to reuse actually pretty old research by Sharon Apple and Cardelli to even when dependencies changed, still reuse parts of the initial analysis. And we also did some other tricks to account for mutually recursive dependencies, because those dependencies easily get stuck when you do verification both ways. In addition, what I didn't show in these slides is that our scopes actually have non-deterministic identities. In these slides, I assigned them easy names, but in reality, they are not so nice. And because the scopes are non-deterministic, we cannot easily compute these diffs in those graphs. So actually that involves solving a graph isomorphism problem, which we also describe in the paper. So if you're interested, please check that out. Of course, we also evaluated this approach and see whether we could get any speedups. The first evaluation we did is using a specification for a large subset of Java, which we applied on a few synthetic projects, some very small, some with more than 100 classes, where each class has 20 methods with 5 invocations of other methods. And we introduced small synthetic changes in these projects. So the results of these benchmarks are shown on the right. The red lines, which are for the large project, generally have the largest speedup factors. It's plotted on the y-axis. And that's of course expected because there's more work to reuse. The speedup factors for single cores executions get up to almost 150 times, which I think is a pretty nice achievement. For smaller factors, those of course drop, and when we use more cores, the speedup factors also drop a bit, which actually shows that incremental analysis and parallel analysis are sort of complementary to each other. However, we also tried a bit of different setup. Instead of introducing small synthetic changes, we sampled commits from some real-world projects. In our case, the Apache Commons CSV, IO, and length 3 projects. We chose those 3 because they have very different sizes. The CSV project is only a few classes, while the length 3 project has over 200. And you can again see in the graphs that for small projects we don't have very much speedups, but for the bigger ones we grow up to a factor 20, which I think is nice again. However, we claim to be language parametric, therefore we cannot suffice with only evaluating Java. Therefore, we took a specification for a very different language, a domain-specific language that our group also develops and maintains, called WebDSL, which is used to implement web applications. Therefore, for that language, we took 2 internal applications and also applied our type checker on some commits of those. And those showed a similar pattern. For the large number of projects, we got speedups up to 16, and for the smaller project, it was like 8. So that to conclude this talks, I think this shows that we can use scope graphs actually to allow effortless incrementalization of type checkers. For the language designer, nothing changed. We still write very high-level specifications, but now suddenly we generate type checkers that are incremental. And I think this is an important step to synthesizing type checkers of high quality automatically from very high specifications. Thank you, and I'm happy to take any questions.
Thanks for the talk. So I see how you can generate these things, and I think it's important for a type checker and compiler to tell me not only that I am wrong, but also how I am wrong. So can you say whether it's with Statix and this, you can explain the errors in terms that this makes sense in the programming language?
Yes, definitely we can. So the implementation is that we have a constraint solver that does top-down constraint evaluation, and whenever a constraint is stuck, it will generate an error message from there. And actually in the specification, it is possible to associate user-defined, or well, specification writer-defined error messages to particular constraints. So if a constraint is failing, the solver will pick that template, fill in the local meta variables, and generate nice error messages. Yes.
So I'm curious sort of about the baseline performance. So I don't think you mentioned here, does adding incrementality slow down the original tape check? And sort of an unfair question to go along with that is, why is the baseline performance as poor as it is? Do you have any insight onto that? Because in theory, if that's fast enough, maybe we don't even need incrementality to begin with.
Yes, so that's 2 questions. To answer the first one, the initial analysis hasn't become slower because of this. The only thing that's required for this approach is just tracing what queries are executed, and that's the overhead that causes is negligible, both in terms of runtime and in terms of memory consumption. So I think that's actually a pretty nice achievement for this approach. To answer your second question about the baseline, the absolute numbers, there are very many details about that in the paper. From the top of my head, it's for the very big Java project, it's a little over a minute. For the smaller projects, it's a few seconds. And why it is slower is basically because constraint solving just adds a lot of overhead over just the direct computation. There's all sorts of different things going on. There's a lot of unification in there, which is not strictly necessary. So in this approach, there are very many ways to pursue optimization, but those are mostly orthogonal to what we did in this way. I mean, if we would pursue them both, I'm sure we can, pretty sure that we can get the type checkers with compare with runtimes at least an order of magnitude within handwritten ones.
Thank you for the talk. My question kind of connects to the previous question, but it's a slightly different take of it. With incremental, I think what you want to achieve is for a small change in input to have a small effect on the output. And so I was wondering, so I think you said like you introduce small syntactic changes to the programs and then measure the speed of, for example, like for what incrementalizing release. Did you also check like how much of your intermediate representations, for example, were affected by the change that you had to regenerate, for example, or repopulate like in the system, or did you like just measure the speed up? And the question is because it relates to the performance question. If, for example, if you do that baseline performance, for example, you could probably have big wins, even for example, if lots of your internal representation like changes and needs to be repopulated.
So we didn't try to quantify the size of the changes that we introduced. That's mainly because our approach has a compilation unit granularity. When something inside a unit change, we recompute the whole unit. Strictly speaking, our approach is not tied to having a file as a compilation unit. You could extract more units from a file, but we, at the moment, didn't implement it yet. That would be an approach with which we can perhaps even attain better speedups. Does that answer your question?
Kind of the data offline as well. And a slightly different question about, I missed was so you're doing dating about granularity. So maybe I didn't catch it. Like, is it a module scope level?
So indeed we compute the diffs of the scope graph, and those are indeed at scope or edge level. So we detect every single scope that's added or removed, and every single edge that's added or removed.
Okay, thank you.
One last question. While we switch over, perhaps? Okay, sorry for harping on the performance aspects, but I think as SLE you gave talk about using specification. So I was wondering, kind of as a follow-up question on comparing this baseline, could you use that specialization technique to also kind of reduce the need for all the things that are going on? You mentioned communication and so on, to kind of improve the baseline performance further?
So I should mention that this evaluation also included the information that I presented at SB. So I didn't turn it off to get back to the here and not achieving that. In essence, I think that one of my potential future directions is me pushing the SB approach more. Why not do that? We need to watch these figures and how they evolve, because well, incrementalizing a smaller cost would change the
Great. Let's take our one more time.